So think about taking the derivative of a function x squared plus 3, y equals x squared plus 3. Y prime is 2x. What if you took the derivative of y equals x squared minus 5? Y prime again is going to be 2x. So we have this problem that we haven't always had when we're trying to undo operations in the past. If I try to undo differentiation, for example, if I tried to undo the fact that the derivative of y prime is 2x, I can't actually figure out why, because maybe y was x squared plus 3, maybe it was x squared minus 5. I don't know, so I have this plus c, this constant I have to add to show that I don't have enough information to nail down exactly the function I'm thinking of whose derivative was 2x. We said if we have an initial condition, if we have an ordered pair on the function we're trying to find, then we can figure out c, and we can give what's called a particular solution. Before we have an initial condition, though, the best we can give as a solution to a differential equation is called a general solution with the plus c on the end. All right, so go back to y prime is 2x. If I don't have an initial condition, the best I can give as an answer, as a solution, is that y must be x squared plus a constant. So what would this look like if you tried to graph it on your screen? Well, I know what x squared looks like. X squared is a parabola, and its vertex is at the origin. What I just drew is x squared plus 0. There's an x squared plus 1 that would look like this. Of course, there's an x squared minus 3 that looks like, that looks like this. And there are infinitely many of these parabolas. I'm sure you would draw a much neater picture than I'm able to draw. You would imagine infinitely many parabolas whose vertices are on the y-axis. Just scoot it up or down, 1 space, 2 space, half a space, radical 3 of a space. So a bunch of stacked parabolas. We will be solving some simple differential equations in this class. You might remember that I said you might take a class in college called differential equations, in which you will explore solutions to more and more increasingly difficult differential equations. One tool that you might use in that class, and a tool that we're going to use in this class, is called a slope field diagram. A slope field diagram. A slope field diagram is a tool, it's a diagram, it's a picture for helping us see the solution to a differential equation, even when we haven't actually solved that differential equation yet. So you see on your notes paper, there's a place for you to draw in a slope field diagram for the differential equation dy dx equals 2x. Now the picture I'm about to show has, I think, fewer dots for you to put slope pieces in, but I think that you'll be able to follow along and fill in that blank graph on the left-hand side as we go through a slope field diagram for y prime equals 2x. Equals 0. Now, a slope field is a way, it's a technique for making a sketch of a general solution of a differential equation without actually solving the differential equation. So here I have my differential equation. Notice this says y prime equals 2x. To me that says slope equals 2x because derivative means slope. So pick any ordered pair on our graph. So we're going to start with 0, 0. I'm going to use 0, 0 as the inputs to the slope function. So y prime equals 2x. I'm going to plug 0 in for x. There's no place to plug in the y, and I find out that y prime is going to equal 0. So that means when x is 0 and y is 0, so at 0, 0, the slope of the solution should be 0. Well, what does the slope of 0 look like? It looks like a teeny tiny horizontal line segment. So that's what you're going to do. You're going to come here to 0, 0, the point you started with. And since the slope is 0, you're going to draw a teeny tiny line segment with slope 0. Now we'll move on to some other ordered pair. So at 0, comma 1, I plug in 0 for x, there's no place to plug in the y, and I get y prime, again, is going to equal 0. So at 0, comma 1, which is here, I'm going to come and I'm going to, again, draw in a teeny tiny line segment with slope 0. This is me drawing in, essentially, the tangent line approximation to the actual curve. I'm using small lines because my tangent line approximation isn't good very far away from the point at which I'm using my approximation. So I'm going to fill up a whole screen with this. If I come to 0, comma 2, again, I'll find out that the slope y prime is 0, so I'll put that itty bitty 0 slope line in. And I'm keep going until I fill in my whole coordinate plane with these teeny tiny slope segments. 0, comma 3, teeny tiny horizontal slope again, horizontal slope segment. So it turns out that for this differential equation, y prime equals 2x, it doesn't matter what I plug in for y. If x is 0, the slope is 0. So you can see I have these parallel horizontal line segments representing 0 slope. So now I'm going to move to a different place on my graph. If I let x equal 1 and y equal 0, I plug in this 1 in for x. There's no place to plug the 0 in, and I get that my slope, y prime, should be 2. So I'm going to come to this ordered pair, 1, comma 0, which is here. I'm going to draw a teeny tiny line segment with a slope of 2. So you're going to have to remember the relationships, sort of the relative relationships between slope 0, slope 1, slope 2. What does a negative slope mean? And again, I'm going to continue until I fill in my whole coordinate plane here. On an AP test, they don't usually ask you to go to more than 9 or 10 ordered pairs. So we just have so many ordered pairs in this one, so you can get a hang of what a slope field looks like. So I noticed I saw a pattern that once I plugged in 1 for x, it didn't matter what I plugged in for y, my slope was going to be 2. And I can continue when x is 2 and y is 0, plugging in this 2 for x. There's no place to plug in the 0 because y prime doesn't happen to have a y in it. And I get that the slope is going to be 4, so I'm going to draw a steeper slope segment. Notice that that's still going uphill. It's only a positive slope, but now it's even more positive, so it's steeper. And you're going to come to every ordered pair in the graph you've created and fill in a little tiny slope segment. So notice here, when x is negative 1, it won't matter what y is. I'm going to have a slope of negative 2. Remember, negative slopes come downhill. Alright, this is my slope field diagram for y prime equals 2x. Notice, if you think back to that picture we drew a few seconds ago of all the possible solutions, y equals x squared plus 2, sorry, x squared plus c, you can see the relationship. If you pick a point to start at, you might think of it as an initial condition point, you can imagine starting at this point and sort of letting your pencil follow these little slope segments, and that'll produce a curve, which is a function of the form y equals x squared plus a constant. And you can see that wherever we might have chosen to start, it's chosen as an initial condition, right? So if I start there, there we go. If I had 0, comma 1, 2, 3 is my initial condition, I can sort of follow this horizontally until I pick up this next slope piece, and in this direction, I sort of follow this slope piece until I got to the next point. And you see again, I have another parabola of the form y equals x squared plus a constant.